helped us have the world we have today. Have a copy of one of his books from the 1900s, early 1900s, that was about his alternating currents and information. A genius, well ahead of his time. One thing I like to start out with is what we're dealing with is, electrical power. It's something that can hurt you because you can't see it until you touch it. So it's always very, very important to be aware of what we're dealing with, especially in some of the VFD controls, soft starters, and those things. A lot of them have capacitors in them, so they retain their power, and they tend to have the power there, even though you may have the disconnect switch. So always grab a meter, always check it. I've done a lot of work over the years with the utility companies, and they always start out this way, and I think it's definitely a definite must. A little bit background on myself. My dad started in wind chargers in 1953. From that, he went on to build several companies. Several of them are still in existence today. On the far right is my grandson. He's fourth generation in one of the control panel facilities that are involved in our Fritz family. I've done a lot of work with many of the power companies, doing pilot studies on VFD technology, soft starters, motors, energy efficiency. And from that, I want to share some of my information and things that I found that make it easier for me to look further. I've also done a lot of work with the Electrical Power Research Institute. In 1995, I did a huge project with them on plastic injection molding machines with adjustable speed drives for energy conservation, and determined where they could save money, where they couldn't save money, and the evaluation brought around a pretty good change in the industry, even in the design of the machinery. A very enlightening experience. They studied 15 facilities that we had installed drive controls on, and ended up verifying the energy conservation. What I'm starting out with today is there's a couple patents. This fellow named Nolan, who was actually with NASA, Frank Nolan, had two very key patents that today are very prevalent in the marketplace. One of them was the variable speed drive, which was a patent that was in the 1970s. And then in 1983, he also had developed a patent, which is what we're going to talk more about today, which is they called it a soft start, a power factor controller, current sensing, and I want to go through what basically it is doing, so that we can understand its benefits, and some areas where we can save power that we don't necessarily look at on a day-to-day basis.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability of...
The reason I bring that up is because a lot of the technology, those two patents I was talking about, are all about controlling this AC motor that the power company and utilities produce 60 cycle power, and it's starting and then controlling it so that we can, maintain its efficiency on the basis of the motor itself, of an induction motor. They're relatively very high efficient, especially today with a lot of the newer, NEMA's designs and those things. They've, gotten the efficiency up to about 92, 93%. Some big machines are as clear as high as 96%. Then they can go with, wound rotors, which are synchronous motors, and those end up being, around about 97% efficient. So the real issue is combining it with the applications and combining it so that you also look at the efficiency of the total system, which is the fan, the pump, so that we get that efficiency to where the sweet spot of those given pieces of machinery are, and we get the motors to match it. And so that's why, efficiencies get increased, but it's not percentage, it's power, total power utilized. So originally what was happening is the motor was just simply started. So this just gives a typical starter diagram where you basically had the three-phase motor here, these set of contacts. They were normally a silver set of contacts through a control circuit and a coil. They were basically just, pulling it in and slapping it on. The difficulty with that is that when a motor starts, because it has no, counter EMF coming back off the rotor, it ends up taking about six times the current to start the thing. Depending on load, sometimes it can be a little bit more than that, and also then dependent on the winding and design application for the given application. Sometimes you can get it down to 3 to 5%, but it was a very difficult way of getting that motor up to speed, because it just wants to jump up to all that rotating magnetic field. Then they came up with part winding, where basically you had half the winding and then the other half of the winding came in, and this would cut it roughly in half. Then they came up with the more elaborate ways, which were Y delta start. So you had your motor here, you would connect the connection, so it would basically put, instead of having 480 volts across that section of the power, it would end up putting 277 volts through the combination of how we connected it, in a Y and then back to a delta. Then came about the Nolan device, which was the soft starter, and that's what I'm going to go into more detail today, which is basically thyristors that are in the circuit, that are starting the motor. This technology has been a little bit overlooked more and more today because of the VFD technology that's out there. And I want to explain the differences of how they function, so that we can understand that. And so this is a couple of examples of soft starters, that are out in the market. Basically, they're just a set of devices. We have 3 wires in, 3 wires out, and then control circuits here. They can also talk to networks and back and forth. And this is just a little bit more elaborate one. I'll go into that detail soon. But what it's simply doing is that it is switching the waveform and trimming it. So here's the initial waveform of voltage coming out of the output of this device. And then what we're doing is when we turn it on, we're just switching it on for short amount of time. So you can see the output voltage ends up being this resultant. And so as time goes of acceleration, we're basically slowly turning the waveform on, which in turn, slows the, makes the motor start easier, and we can keep the power down very dramatically as we're going up in speed. And let's see, this is a little bit about the webinar. Let's see, I also highly recommend this organization. It's ESA. My father was a past chapter president and director of ESA. They're out of St. Louis. They hold a class, or not a class, but a training sessions and convention every year. This time it's towards the end of June. Like I said, I can't speak highly enough of this organization. It's a group of electric motor people from around the world that have come together since 1944, developing all kinds of standards and to help increase reliability of motor application. They have all the this little book here I call a little Bible, but it really helps understand motors in a very in-depth way. Also gives you at your fingertips all the formulas for power, CFM, efficiency, and so what I want to talk also about today is back to the soft starting. The advantage to this is that once it's up to speed, it literally gets shunted out. So, and again, this is a contactor internally built inside the units now that actually just shunt these out after it's up to speed. The benefit to that is then we have pretty much zero losses, as the motor is running, which is very key because as compared to a variable frequency drive, when you have to add line reactors to help clean the power up and output filters and the VFD itself, you end up losing anywhere from 3 to 7, 10% of the power. And so I really go back to the issue of getting the design to the point of where it is. So my belief is that on pumping and fan applications, everybody hears the calculation of the cube effect. Yes, you buy a VFD, you're going to save power. It's true, you save power because you get the cube effect on the actual absorption of power, but you can also do that by trimming impellers. So there's a fellow out of Australia that had developed this software that I think is quite unique. If you'd like to send me an email, I'll be glad to link you to him. And he and I have given some webinars over time, but he has about 40 years in pumping experience, and he teaches training classes around the world. And so the issue is that when you slow the pump down with a VFD, you also change the efficiency point of the pump. So it's very key that when we're operating a pump, or fans work very similar, is that when you have a certain flow, there's a best efficiency point of a pump. You can get, you can slide it out a little bit, but it gets a little bit better, a little bit less. But this changes the efficiency point as much as 30%. And so the issue is, if you're not careful, that when you put a VFD on, you can slide the pump out of proper efficiency spot. So it's not at its peak efficiency point meaning it's maybe 70 or 75% efficient. But it can go down to as much as 30 to 40 and 50% if you slide off the curve too far, and then you can get to points of cavitation. So that's where some areas have come into. And then on irrigation, you also have to look at the total acre feet produced to the site. So you want to look at how many acre feet of water you need to get to those crops. That doesn't change, but if you slow it down with the VFD and you go off the curve and get it 20-30% off the curve, all of a sudden those two losses, your total time to get that water and gallonage out to the actual application is quite high. And so I do sell VFDs, but I also recommend that people look at those various issues, because the true efficiency is, and back in time before we had some of these devices, they were actually trimming impellers a lot more. They were being more cautious to the the flow rate and the pressure, and dig a little deeper into the design, go a little further, and you'll find the relationships of the total system efficiency can jump quite high. I know that the savings of doing that, and also then the pipe sizing of your discharge for your head pressures, your filtering, where is that, those filters, how much head pressure are you having to drop across those filters, is also some areas to definitely look into. And again, getting back to where that impeller was designed, the speed, and then its efficiency point, to get at its key point, and then do as much as possible to have that designed to the RPM of the given motor. Again, how much power are we really losing? Again, you've got switching losses, and this is in a VFD. You've got inductors and coils and capacitors that also utilize some power. So this is a typical circuit of a VFD. So we have the diode front end, we have the inductors. They're taking the waveform here, making it to DC, and then moving it back out with IGBT power, which is the isolated gate transistors, and then they're giving it PWM, pulse width modulation. And the key is that when you do that, you create what they call nonlinear current. So you get these pulses, of this is the voltage from the power company, but then this is the current pulses. So what happens is that when it draws power through these diodes on a 6 pulse, you end up getting these blips of current. Well, those create what they call harmonics. So all of a sudden you have, third, fifth, seventh, harmonics. And as you adjust it with load and back and forth, that will change. And then you also, need to utilize special wound, motors in most cases, or put, output filters on them so that this PWM, this is the output PWM of VFD, will not destroy, the peak voltage capability of those windings. And so they're basically just controlling this PWM, negative and positive, building the, building the current waveform as much as sinusoidal as they can, digitally with pulses. This happened to be a main circuit of a, VFD back in time that I had when I was working back with Toshiba years ago in the 80s. Again, it shows the simpler parts of the circuit. Today they've, gotten extremely complex with a lot of their, characteristics, but all of them, pretty much have this, basic underlying format in them. waveform. This is a meter that I've used a lot over time by fluke. It's a 434 scoping meter, and the benefit of this, it actually gives us a real look at those waveforms, so we make sure that the actual motors are staying within tolerance, and also what the true RMS power utilization is. And if you don't have one of these, I just want to share this video. It's got a lot of unique things that can definitely help you with, again, back to efficiency.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using three-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance and harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative.
So what I'm talking about is that the harmonic content of a VFD, this shows the voltage waveform here. This shows the added third, fifth, and seventh harmonics that also go down the line, into a VFD, and then this shows the resultant. So if you use one of those meters, you can also then capture this data so that you can determine what the true RMS power is being used in the system. A standard amp meter doesn't catch these other values, and so your power meter will, and so you'll end up not quite always understanding why things don't match. And so then what's required is you have to put on these filters that are, again, inductor coils, capacitors, that are cleaning up these harmonics here, the third, fifth, and seventh harmonic. It cleans them up, and then it brings it back into line, and it can make a difference on a motor as much as total of 10% power, additionally used by allowing this without in the circuit. Again, you're saving money by actually slowing that motor down, but there's noise and harmonics that are also created into the circuit. So again, if you do want a copy, send me an email. I'll send this off to Rob and your connection to him, and then you can talk to him about getting a copy of this software. You load in the various parameters where you're putting your VFD, and then it plots out from pump data exactly where the pump curve is going to go to. I also have a over time VFD modeling software tool that I can give you that also can help you model the savings. this is an idea of what that screen looks like on the Fluke, showing those input pulses. This is a differential. You can see here that before and after the harmonic reduction, they were pulling 415 volts at 138 amps. They put the reduction on and they brought it back to 443 here and 128 amps. Well, if you do the math on those two, you can see that is roughly about a 10% difference. But 10% difference at today's power cost is quite a large number. Again, the other thing is that when you go back to this ESA organization, you can also get access to this motor winding failure analysis, so you can determine what's going on. So this analysis here shows a spike of high voltage, which could have been coming from a VFD that got surged into the motors. That's why you need spike resistant wire in your motors. It showed short here. This showed a single phasing situation. This showed a slot insulation failure, and again it goes phase to phase or on the far right. But it's a very handy tool to tell you tell you and see what's really going on. Just a little bit more about some VFD stuff. So back to the soft starter, I feel is a very, and what kind of I want to bring up today, is the most efficient way is to get all the losses out, all the harmonics out, once it's up to speed. But you have to go dig deeper and make sure that your motor and your pump is running at the auto efficiency. That is where you pick up major efficiency gains, because you need total GPM. It's not just simply I put a VFD on and I'm saving 30% power. You may be, because that's at the speed spot it is, but you have to really look at your total work performed. And so again, keep it going. So this is a little quick setup of a soft starter that is available onto the market, that you can easily ramp the motor up to speed, soft start it, and it actually gives you a little bit of detail of how it functions. You'll notice here that this shows the actual circuit, from the power source onto the motor, and then it shows its current setting and all this. But you noticed here that while it was running, you saw the pulses, of power, meaning that it was only allowing the switching of the power slowly. And then as it got up further and further up to speed over acceleration time, came across to running. When you saw let's see if I can move this back here a little bit. When you see it here, still running before the contactor, you can see that it's automatically regulating again the power and the current to the motor. So the average power, is less while it's still in this running mode. What that means is that the load still did not require the motor to be giving it full power. And that's where your power factor goes off, is when a motor becomes less and less loaded. So this is how it controls the power factor. It brings it much more, into a line to 96, 97%. And in some cases, if the motor is actually, lighter loaded, this has a sensor where it actually, monitors its current when it's lighter loaded. It actually brings the thyristors, back in to save power. Even while it's running at full speed, because you're average, and it can run as much as on a motor that's not fully loaded, or let's say a throttle of a pump happens, gets throttling, it actually can bring back the power draw of the motor, as much as 15-20%, total required. So it is important to understand what they're doing with this technology. So it's back to the point of the technology. Is a much simpler device, a much less expensive device than a VFD, and it is very efficient in its running mode. It also doesn't create the harmonic content, and it also on the input or the output, and so the motors don't again have to be have the high special winding, insulated bearings and all those things, which also add into cost. Let's see. So to kind of give a rundown of my points here is that there's added losses in VFDs that sometimes are not shared, and you need to be aware of them. Also, the efficiency of the fan and the pump curve, change. So you got to be aware of those losses by them not being at their optimal point on the curve. So total system efficiency, and then on irrigation systems is definitely look at the total acre feet of water that you need to get to the crops. Because if you have to run it, you are running it slower, and yes, it looks like you're saving power, but if you have to run it, 5 hours longer, it's kind of, all for naught. And again, the cleanness of the waveform, and then, I do advise, getting involved and checking some of these, details and available, that ESA has available. If you want to, get access to that stuff, let me know. I can connect you with some people in the industry that I know. Again, if you want copies of the, software here for VFD applications, prior to purchase, of the thing, to keep the pump into the optimal efficiency point and make sure that that's checked. There definitely are areas where, imbalances of, the pump being at the wrong space and time or whatever, You can correct some things with a VFD by overspeeding and underspeeding, getting it back to this point also efficiency. So, do look at those, those points also. Again, this is some stuff that I give on another class that I talk about a lot more further on, VFD technology, but harmonic spectrums. And this shows a few different meters that are out there. Your standard voltage meter, your true RMS. These range anywhere from $5,000 to $7,000 for a true RMS meter, which reads similar to what your power meters do. And then there's the simpler ones that you can monitor over time. It's good to get do calculations before as you design a system. This is my contact information. Let's see here if Barnaby had a chance to jump in. Not sure if you're here. If you raise your hand, Barnaby. Looks like he wasn't able to join us today, but he does join quite often with me. He and I collaborate on a lot of different details on a lot of different types of projects. And I'd like to, open it up for discussion, open up your mic, and, please ask questions. I'm pretty much, finished with this presentation at this point.